In this video today, we're going to look at volumes of solids with certain shaped cross sections. I have a series of videos on solids of revolution. That's different. These videos are not on solids of revolution. I think I'm maybe going to break this into a couple videos. We'll see how it goes. I had a series of 5 videos looking at a region that we revolved, every which way to make solids of revolution. This is going to be the other types of solids that we do in AP Calc, both AB and BC, solids where you have a region in the plane and you have certain shaped cross sections perpendicular to one axis or the other. And that's what we're going to focus on today. It's very formulaic. Once you get we're going to talk first about the big idea, how to construct these, like how to think of them. And then we're going to go through and really just make it formulaic, make it easy, something you can study. It's good to understand where it comes from, so you can kind of adapt to a different situation or figure it out again if you forget a formula. But it's also it's very repetitive. There's a pattern. Once you understand it, it's not hard. So the problem we're going to look at is going to involve these two functions shown here. The functions f of x and g of x. F of x equals the natural log of x plus 2, and g of x equals x minus 1 quantity cubed. And my first thought when I see these functions, and maybe it's because I wrote them and I wrote the problem and I was planning this, but my first thought is, hey, I think those are both one-to-one functions. They're both strictly increasing, which means they have inverses, which means, when I make this region, when I look at the graph of it, I'm going to be able to solve each equation for x and do these not just with vertical cross sections perpendicular to the x-axis, but also with horizontal cross sections, so they'd be perpendicular to the y-axis, like some of these problems. So before you even read the questions, you might be expecting to get both. And maybe you don't see it just in the algebra, but let's look at the graph. Here, if I go to y equals and plug these functions in, and my window for this is -2 to 4 for both x and y. That's what I'm graphing it on. And there's my region. The blue graph on top is the natural log graph. That's f of x. The red graph is the g of x, the lower graph. So I have f on top, g on the bottom here. And when I'm going sideways, I have g on the right and f on the left. So when we're going horizontally, the red graph is the bigger x value, and the blue graph is smaller. And when we're going vertically, it's the other way around. So that's important to realize. In fact, here, I did throw this in Desmos as well. And there's our graph. Just get that out of the way. Here, we can just get rid of that. And I have the intersection points here as well. On Desmos, you'd want to do that on the graphing calculator, get those values and store them, at least the x value, maybe the y value too. In fact, let's do that right now. When I graph these, if I'm doing this on an AP exam or a calc test, I know I'm going to need limits of integration. And, in this question, it says the region S is the region bounded by f and g. There's no vertical line boundaries. We're not told between x equals 1 and x equals 2 or something like that. This is it's just between those functions. So what that means is it's the entire region enclosed here. And so we need those intersection points so that we have limits of integration when we integrate. Okay, so that's what we need to do first, get those intersections. So on your graphing calculator, if you have a TI, obviously, you're going to do the intersection tool, second trace, the calculate menu, choice 5, intersect, and then enter, and you can just hit enter again to get one of them, or maybe you want to get the one on the left first, so maybe you type in 0 for a guess, and there it is, 0.0588. For the AP Calc exam, you need 3 decimal places, so 0.059 would be good if you want to write it down. However, I can't stress this enough, you do not want to use 0.059 in another calculation, because while 0.059 is accurate to 3 decimal places, it doesn't mean that if you use it in a calculation for something else that will be accurate to 3 decimal places. You can get rounding error. So what you want to do I mean, you could write down a bunch of decimal places and type them in, but the better thing to do here is store the value. So that x value, and actually we could store the y value while we're at it too. So I'm going to have the x values be a and b, so from a to b, and I'm going to make the y values be c and d. So I'm going to make that y value c and that x value a, and the way you do that on the calculator, if you don't know, is you quit out of there, and I'm going to say x, so I hit the variable button, and I'm going to store it as a. So that x value of that intersection point. And then I'm going to do y, so I'm going to hit alpha and then 1, because that's y. And I'm going to store that as as c, because my y values are going to be c and d. So I have the first intersection point stored as a comma c, and I would write that on my work too. I would say you actually want to show that you're setting them equal. So you want to say f of x equals g of x at x equals, and I would say a, which is approximately 0.059, and at x equals b, which is, and I don't have that one yet. And then for the y value, I'm going to say f of a is c, which is that value I just had, negative 0.834. And then I want to do the same thing when I find the other intersection point, f of b. I'm going to call that d, and I'm going to put its y value there. And now what I'll have are limits I can use. I can use a and b for anything horizontal, for any x value limits that I need. Anything horizontal is not the best way to say it. For any integrals that need x value limits, we'll talk about that as we're doing this. And I can use c and d for the ones that are going horizontally, where the cross sections are going horizontally, and we're going about perpendicular to the y-axis. Then you're going to use y value limits of integration, so I'd use c and d. The point is, I'm actually just going to write a and b and c and d once I have these defined. I don't have to write these little values, and in my calculator, if I have to compute them, I can just use a, b, c, and d. So to get the other one, back to the graph. Second, trace, choice 5 is intersect. Enter for the two curves, because I only have two curves graphed. This one's closer to like between 2 and 3, so I could just say 2 for my guess. Should put me there. There it is. 2.424 roughly for x, 2.885 for y. Again, quit out of here. I'm going to store x, so I hit the variable button, as b now. And I'm going to store y, so alpha 1 for y. I'm going to store it as d now. And there's that. So I have A, B, C, and D now stored in the calculator. And B and D, again, we're about 2.424 and 2.885. So I'm going to write those on my paper. 2.424, 2.885. And I'm going to be using, again, those A, B, C, and D values as my limits of integration as we do these problems. All right? So what now? We need to find some volumes. Now, often a first question is to find the area. I didn't put that here like for A or something. But if we wanted the area of the region here, and then it's called region S, right? So S is this region in here on the graph, right? That's what we're looking at. And I'm going to get rid of that now because I want to draw my base of my square there in a minute. But if we wanted the area, you could go either way here. You could solve both of these equations for x in terms of y and go with horizontal cross sections, or we can use the functions as given and just do f of x minus g of x to get that vertical distance between them and integrate it from A to B. And since that's already set up to go, if I was asked for the area, that's what I would do. I'd just do the easiest thing. So here, I'll write that down. The area of region S is the integral from A to B, that's a B, of f of x minus g of x dx. Okay? Now, in part A, it's going to look a lot like that, actually, a lot like what I just wrote, because we are going perpendicular to the x-axis in part A, which is how I had my rectangle go in that area I just did, right? So the idea is, let me draw that a little better. If I want square cross sections, the idea is this distance here at every x value along this interval, the distance between the two functions, is the base of a square. It's the side of the square. And the square comes out of the screen at you. So when that distance is longer, it's going to be a taller square. And when it's shorter, it'll be a little shorter. And it goes down to a point over there. And I have a tool where I can show you a little better what it looks like three-dimensionally, something I made on Desmos. So let me pull that up here. And I have the functions in there. That's that region. And for square cross sections, perpendicular to the x-axis right here, that's going to be the solid. And this blue stripe here is one of the little cross sections, like a little square disc. Right now we're looking straight down at the xy plane. If I tilt it a little there, you can see the height as z coming up. And it's kind of a weird little shape. Might be easier to see actually if I take out the solid for a second and you just look at the square cross section. So if I'm looking at it from this kind of angle here, you can see how that's a square. And that square cross section, we can slide it through this region. And as it moves through, it kind of fills out the whole solid. Good. And here, let's do that with the solid there. Here is that cross section going through the solid. And that's what it looks like. So that region S in the XY plane is like a flat bottom, like base for the solid. And then that solid's coming out of there. And it has square cross sections, but it has some nice smooth curve to it as well. The squares do give it those kind of corner edges on top, though. Those are the 90-degree corners of the square going vertically. So the idea is, my mantra, I have like a catchphrase for each unit in my calc class, is to, for this one, it is to find these volumes, you're going to integrate the cross area. Okay? The dx or dy, the differential part, of these little cross sections, right? And when you integrate, what it does is it finds these volumes by taking the cross-sectional area, the thing I'm saying to integrate, and multiplying it by that differential dx, right? So the area times dx gives it a volume, right? It's an area times a thickness. So that's the volume of that blue disk is the idea. And then the integral makes that blue disk super duper thin, arbitrarily thin, and it adds together infinitely many of them going across the solid. So you're adding together infinitely many, infinitely skinny little square disks to give you the volume of the solid. And that's the big idea. All right, so what does that look like? Well, the area of that square that we need to integrate, right? Integrate that cross-sectional area. The area is just the side squared. And the side of that square, if you look down in the region between those red curves, it's just the top curve minus the bottom curve, right? That side of the square is always, it's f of x, minus g of x, that distance along the base. That's the side. So to find the volume, that's all we need. We need f of x minus g of x, and we're going to square it. So here's f of x minus g of x, right? And then we square that entire part. And that's the cross-sectional area. When you multiply it by the differential dx, that's what makes it have that thickness. And with the integral symbol, that takes that dx, it makes it like infinitely thin, arbitrarily thin, but it also makes infinitely many of them and adds up all the volumes. That's it. That's how you make this volume. Okay? So we're going to do, we're going to do a semicircle as well. I'll do that on this video as well, and then I'm going to stop and get into some of the other solids on a second video. So let's look at the semicircle. The semicircle is perpendicular to the y-axis, and this the way I set it up. It could be any though, right? You could make the square be perpendicular to the y-axis, the semicircle perpendicular to the x-axis, doesn't matter. The point is, and actually at the end too, at the end of the last video, we're gonna put together a list of all the shapes and the coefficients and the two things to pay attention to as far as horizontal or vertical cross sections and what that means for how to construct these. But I think you'll see the pattern too as this emerges. So perpendicular to the y-axis, that means we're going to go horizontally now. And instead of being the side of a square, this is going to be the base of a semicircle. It's going to be a diameter of the semicircle. So the semicircle comes out of that region like that. Let me show you my Desmos tool again, because that'll do a better job than my drawing there. So back to the XY plane. That blue cross section right now that we have is going vertically. If I wanted that square to go horizontally, perpendicular to the y-axis, it would instead look like this. Right? Now it's going horizontally, okay? But I don't want a square right now. I want a semicircle. So semicircles perpendicular to the y-axis. There's the cross section. Oop. Try that again. Having some technical difficulties here. All right. In the wrong one. Here we go. All right. Semicircles perpendicular to the y-axis. If we kind of tilt this down, you can see how it really is a semicircle. There's that slice filling through that solid. And, you know, when it changes like how the slope gets really steep for a minute there, that's where you get these really wide-looking parts just because of the way it's going. But, yeah, if we put the whole solid there, that's what it looks like. And you can kind of see those semicircles. So again, the idea here is we just need to integrate that cross-sectional area, right? And so with the semicircles, we just need the area of a semicircle, right? And a semicircle it's obviously half a circle. So the area of a semicircle, I'm actually going to go to a blank page here for a second. The area of a semicircle, that's a semicircle that I'm drawing there, is 1/2 pi r squared, right? But the thing is, on our circle, our semicircle, we don't have the radius, right? We have this length here, and that's the diameter of the semicircle. So you want to think, if I'm doing 1/2 pi r squared, but what I really have is the diameter, then I need to divide it by 2 to get the radius. That's what I'm going to square. So it's 1/2 pi times the diameter over 2 squared. And you could just, you know, do the one curve minus the other curve for the diameter and divide by 2 and maybe even simplify inside of the square. You could do that. But there's a good reason to not do that and instead to do a little algebra here first. If we take that 2 on the bottom and square it, it's a 4 on the bottom, and this is equivalent to pi over 8 times the diameter squared. And this is the formula I'm going to use. The reason I want to use this for the area of a semicircle, and this is the diameter, right? The reason I want to do this is because this makes all of these solids so formulaic. The fact that the dimension I'm going to use is just the distance between the two curves, the distance between f and g, or g inverse and f inverse, right? I'm going to subtract those two curves and I'm going to square them just like I did on the square. And the only difference here is going to be that we're going to multiply by this coefficient, pi over 8. If you understand it this way, it gets really easy to do these volumes. All right? So, without further ado, here's what it looks like on the semicircle and perpendicular to the y-axis. Okay, so you have a couple things to point out. First of all, we have the pi over 8 out front. You know what? The fraction bar isn't showing up there. Let me resize this a tiny. There it goes. Okay. So we have the pi over 8 out front. That's that coefficient I was talking about. We have the two curves squared. So the difference between the curves squared. And then there is another difference here that's important. Oh, and there's a mistake I'm realizing. The limits of integration here are wrong. They should not go from A to B. They should go from C to D. And I'll have that fixed at the start of the next video here with the other ones, but forgot to change that in my copy and paste. But you'll also notice that we have G inverse minus F inverse instead of F minus G like we had there. So that is because those changes are because we're going horizontally. We're going about the y-axis. So when it's horizontal, it's three things you got to watch. So because it's perpendicular to the y-axis, it's going to change those limits of integration. Those are y values. It's going to change this differential. That's a dy. And it's going to change the functions. Instead of f of x and g of x in terms of x, we're going to do g inverse of x, or g inverse of y, and f inverse of y. So it's going to, we want those functions in terms of y, which actually we should solve for those as well. You can't just use like g inverse on an exam like that without showing what it is. So we'll do that work in a second here. You don't have to write it this way either. You don't have to write g inverse and f inverse. You can actually write the functions in terms of y after you've solved for x. Okay, so that's the other piece of this. Let me go through that really quickly. This f function, if I want to solve it for x, I would just, I have y equals natural log of x plus 2. Subtract 2 from each side. Y minus 2 equals the natural log of x. And then exponentiate with base e, right? So I'm going to get x equals e to the y minus 2. Okay? And then I want to do the same thing with g. So I'll use a different color here. With g, I have y equals x minus 1 quantity cubed. And I want to solve for x, so I'm going to cube root both sides. And then add 1 to both sides. So x equals the cube root of y plus 1. And those are the functions I'm going to use. So when this says g inverse of y minus f inverse of y, these are what I'm using. It's going to look like this. It's going to be g inverse was the cube root of y plus 1. And then f inverse of y was e to the y minus 2. So it'll be minus e to the y minus 2. Okay? And that's, you can write it like that in there, or you can write it like this in there, as long as you clearly define what g inverse and f inverse are. So let me actually show how I would write that, because I like function notation. If I'm given function names, I'll use them. And if I'm not, sometimes I'll just write them myself, right? And that's kind of what we're doing here. So let me show that really quick. If I say, from doing this work, I can now say, here, I'll write it over here. F inverse, I should be consistent with my colors here. So I guess this, right? In other words, F inverse of y is e to the y minus 2. And this one, g inverse of y is the cube root of y plus 1. Okay, sorry, cramming it in here. But if you define these in your work, then you can use them, right? You can use g inverse of y and f inverse of y as you write it out. And if you're wondering, do I have to use y then if I name it as a function? No, you don't have to. You could use any variable you want once you define a function as long as you're consistent, as long as the variable in here matches the variable of the differential, it's correct. So you could even put x in there and it's still true. I'm sticking with y though for clarity. I want to be very clear to anyone that we're going horizontally here with this cross section, right? We're looking at a horizontal rectangle here that is the base of that semicircle. And so the width of the disk, of that semicircular disk, this little width here is a change on the y-axis. That's why it's a dy. So that's why I don't want to change those variables. Okay, that's going to be the end of this video. We got through square and semicircle. I'm going to go a little faster in the next one with the shapes, and we're going to just kind of get through the rest of these shapes here. Right isosceles triangles going a couple different ways, with the hypotenuse in the region, with the leg in the region, equilateral triangles. And at the end of the next video, we will put together a list of all these different shapes. And there could be others, but these are the ones I've seen on the AP exam and in calc books. And we'll just list the coefficients and look at, again, what the key differences are when it's horizontal versus vertical.